Hello, class. This will be the recorded lecture continuation in section 8.3. And now we're going to talk about calculation of determinants of a 3x3 matrix. To do that, we have to introduce a couple new terms. And this is as far as we're going to go. We're not going to do 4x4s or anything like that. And so the two terms that we are going to introduce is the first term is called something called a minor. And the definition of a minor of, say, a 3x3 matrix is that you cancel out or get rid of, is maybe a better word, one row and one column. And you see what is left is a 2x2 matrix. And you actually calculate that determinant of what's left of the 2x2. So the slide does a good job, so I'm going to leave it up here because it's easy to show you the cancellation. So let's take this matrix here and calculate minor 1, 1 and minor 2, 2. So to do that, if minor 1, 1 means that we cancel row 1 and column 1. So you see what's left is this little 2x2, which is 5, 2, minus 3, and minus 4. And when you calculate that determinant, you do the calculation just like we did in the last lecture, and you could see you would get minus 14. So how would you do 2, 2? Well, in this case, you would cancel out row 2, column 2, and so you're left with these four numbers, right? Minus 2 and minus 1 in the first column, and minus 1 and minus 4 in the second. So if you calculated that, minor, you would do the determinant of that, and you would see that ends up being plus 7. So that's step, new term number 1, minor. We're going to introduce one more term, which is called a cofactor. And what a cofactor is, whoops, I missed the definition here. What a cofactor is taking the minor and adding a sign to it. And what we mean by the sign is these are going to be a plus or a minus. So you see this definition. We have this minus 1, and then you take the rows and columns and add them together. So if this number is even, right, if it's like 2 plus 2 or 4 plus or 1 plus 1, then the minus to a square power to a fourth power turns positive. If the row and the columns add up to an odd number, then it changes the sign of that determinant minor to a negative. So what I'm going to do here now is put this back to the regular size. And what we're going to do is to calculate 3 cofactors in this matrix. I'm going to put it on pause and put the matrix up on the whiteboard. Okay. Now I have the matrix up on this whiteboard here, and let's first calculate what we call cofactor 1, 1, which is row 1, column 1. And so unfortunately, I'm going to have to do a lot of pausing, but I think it's important to show you. So we're going to cancel this out here and this out here. And so what's left is determinant 5, 2, minus 3, and minus 4. And we did that already, so that would be 5 times minus 4 minus 2 times minus 3. So what would that be? Minus 20. We have 2 minuses, so that would be plus 6. And so that would be minus 14. So that's the determinant. This is the M11. But now we have to calculate this minus 1 to the I plus j, which is 1 plus 1 up here, right? So when you do that, you get minus 1 to the 1 plus 1. And so that's minus 1 squared. And that turns it to plus 1. So plus 1 times minus 14 is, again, just minus 14. So I'm going to put this up here as we're going to use it later. 1, 1 equals minus 14. Okay. So let's calculate cofactor 1, 2. So again, I paused it so I could get rid of those lines because we're going to put new lines in here now. So what we're going to do now is, again, still cancel row 1, but now we're canceling column 2. So the first thing we're going to calculate is the minor 1, 2. And that would be 4, minus 1, minus 3, and minus 4. So when you do that, you get 4 times minus 4, and then minus a minus 1 times minus 3. So that looks like that's minus 16. We have 3 minuses, so that would be minus 3. So that would be minus 19. And so now you want to look at minus 1, and this would be 1 plus 2. So this is minus 1 cubed, which also equals minus 1. So you take minus 1 and multiply it by the minor, which is minus 19, and you see you change the sign of that one, and it ends up being plus 19. So that would be A12 equals 19. Okay, so let's calculate A13 now. And so when we do that calculation, again, let me cancel these out. And so we're going to cancel out again row 1, but now we're going to cancel out column 3. And so the minor 1, 3 would be 4, 5, minus 1, and 2. So when we do that, you get 4 times 2 minus a minus 1 times 5. So that would be 8 plus 5, and it looks like that would be 13. So we again look at this would be 1 plus 3. For the sign change here, it looks like that's an even number. And so that would be 1, and 1 times 13 equals 13. So A13 will give us 13. So hopefully that gives you a good feel for how to calculate these minors, or excuse me, these cofactors. Okay, so why are we doing these minors and then the cofactors? Well, here's the definition of calculating a determinant of an n by n, but we're again just focus on a 3 by 3. And so the idea is that we define the determinant as follows. Choose any row or any column, and then multiply each element in that row or column by its cofactor, and then add the results. And again, this value is just going to be a number. The book calls it a 1 by 1 matrix, which is just a number. So it's a little confusing. The value of that determinant will be the same no matter which column or row that you choose. So that's the beauty of it. So that's why with regards to these calculations, sometimes it's a good strategy to decide what row or column you want to pick. And I'll show you what I mean in this example here. So here was the original matrix that we were dealing with. And so I strategically picked, as you can see, I calculated all 3 cofactors for what row 1, right? 1, 1, 1, 2, 1, 3. And so by the definition, the determinant will equal this. So it would be this first element, which is minus 2 times A11, and then it would be plus 0 times A12, and then it would be plus a minus 1 times A13, sorry. And so you see the beauty of this is any number times 0 is what? 0, my favorite number. So theoretically, when you do this calculation, you wouldn't even have to calculate A12, right? Because it would always cancel. So it saves a little time. If you're a computer, you don't care. You just pick the first one all the time, right? But as a human being, we're trying to do the least amount of work as possible, right? So this determinant would be minus 2 times minus 14, And then we'd have, again, as I said, 0 times 19, so that cancels. And that would be plus a minus 1 times A13, which is 13. So this goes away. So that would be 28 minus 13. So it looks like that answer would be 15. And again, you could do it with any one of those rows and you would end up with or any one of the columns, and you would end up with the same answer. Let me show you one more of these calculations, but I am going to use the slides for this. So for example, if you wanted to calculate the determinant of this particular matrix, the strategy would be pick row 1 or column 2, right? Because that's where the 0 is. So theoretically, you would just have to calculate the cofactor for 1, 1 and the cofactor for 1, 3. You don't need to calculate the cofactor for the 0 because any number times 0 is 0. But I took this right out of the book and they did that. So here you could see that this would be A11 times the number 3. This would be A12 times the number 0. And then this would be A13 times the number minus 1. And if you walk through that, you could see the second one cancels. So you don't even have to do this calculation. But if you walk through all this, you would see you'd end up with 122. Okay, so that ends the recorded lectures for calculation of 3x3 determinants. One more left, and then that will be the calculation of Cramer's rule with 3 equations and 3 unknowns.